Really excited today to have the inaugural lecture for the Pulakeshi Dayalu Astrophysics Saturday Morning Physics Fund. And the family is here, and they've very generously made this possible. So let's welcome them. So I'd like to introduce Parveen Dayalu, who will say a few words about this lecture and fund.
Thank you so much, Tim. My father, Pulakeshi Dayalu, was a kind and brilliant man, and he loved Saturday morning physics. He moved to Ann Arbor in 2012 or so after he retired and came here regularly. I'm going to say a few words about him and the series. I came here once with him to a lecture on the Higgs boson, the hunt for the Higgs boson, and as we left, it occurred to us that there had to be a lot of conditions to even go into how a thing like that was even possible. You needed inspiration, you needed idea, you needed government funding, a huge amount of land to build this particle accelerator straddled between two countries, men, women, young, old students all coming together, designing and analyzing the results, and of course, massive feats of engineering, all to hurdle two beams of protons together at high speed, scatter matter and energy, and scientists are still learning from the scatter. So I thought if you think about that a little bit, hold on to that a little bit. In some ways, preconditions all coming together, funneling through in one space, and a scatter of awesomeness. I think as human beings, we could be that way too. It was definitely the case with my dad. Books, that was a big condition, right? He loved education, he loved to read. He had his inspiration from people like Subramaniam Chandrasekhar and Stephen Hawking, and he read widely, worked hard at understanding things, even though he was not a physicist, he was an engineer. Books by Fred Adams and by Brian Greene. And he held on to this inspiration even during the pandemic when it was difficult and the library was half closed. In fact, little known fact about my dad, he discovered the SARS-CoV-2 nebula. Right after this picture was taken, we did get a haircut. Unlike Albert, my father studied ancient Sanskrit verse and language, and this was actually a verse from the creation hymn of the Rig Veda, and it really drew him to the science of the Big Bang and deepened his comfort with uncertainty. It's very lovely. I'll let you read it. He loved being outside. He loved looking at the sky, the sun, the stars, and the outdoors, of course, especially tennis. Tennis bonded him to people, many of whom are in the audience, and tennis invigorated his mind. And he always talked about how Newtonian mechanics was insufficient. And I now realize it's because of those occasional serves that he swore was going to go in, but somehow, it must have been twisted space-time at the corner of the service box, clearly. He had a lovely, whimsical, colorful garden, and this was a space for him to be quiet and think and work on his own. And of course, a big condition for him was a family that was large and loved to learn and loved to talk. This is my dad there with his family in Bangalore, India. This was a family he was born into. And as a young engineer, he was surrounded by pioneers in medicine and law, science, and gifted musicians, and really he was very fortunate. And that's me there in the front. He immigrated to the United States, where he worked as an electrical engineer for GE and Boeing. And we were a very close-knit family, a loving wife, kids who adored him. Really, really blessed. He always kept in touch with extended family, and this was a very pliant group. They were always willing to listen to his musings on physics, and so he always got an ear to explain whatever it was he was thinking about. And in this kind of boisterous company, somehow he managed to find a way to really explain things in a simple way, things that he learned here. Occasionally, we're quiet enough to shut up for a picture, but that doesn't usually last very long. So we inherited Dad's salty sense of humor, for sure, and that is an actual quote. And then there's his grandkids, Rajan, Malini, and Sheila, who are here, and who put the stars in his eyes, even without a telescope. And then there's Saturday morning. He needed Saturday morning. So he moved here, and he every Saturday morning, he would get his duffel bag, he would get his little notebook in there, and he would wear this hat, which basically kept the polar vortex out and kept the physics in. But he would hop on this warm bus, which would bring him right here to Church Street on time, except when it wasn't. He did not like the overflow room. And he would show up, and at the top there, there was coffee and bagels, and there was a warm smile and greeting every time from Carol Raybuck. Folks, Carol has set up this entire lecture series for years and years and years. She runs it. She is amazing. She still remembers my dad and his smile. I am beyond grateful to Carol. And also, Dad would... Thank you. Thank you. And Dad would sit here, and he would try to get a seat closer to the front. And after these lectures, he would wander down to speak to Fred Adams often. And Fred was always so patient. He would tell me he answers my questions, and the questions are silly, but he answers them. And so it's little things like that kept him coming back over and over. And I'm sure it's the same for many of you. So a place like this, it's not proton beams colliding. It's ideas and knowledge and insights. And what scatters is awesomeness. And there's energy and matter that my family and I are still enjoying and benefiting from and learning from. In the case of my dad, quotes, expressions of simple, wide-eyed wonder, amazing stuff. That was something that he always said. Perspective. We whine about something that happened at work or in the neighborhood or something, and it was like, well, oh yeah, but he always told us about something bigger and cooler than that, which is really refreshing. Integrity. When he came here, he came to expect that physics should be held to a high standard, as should his kids. And he told us stories about this, from the history of science. And then, of course, his own accelerated particles, who are growing and learning and inspired by that level of curiosity on their own. And finally, he left matter. Actually, he took a lot of notes, created. We're still going through his notebooks from writings from attending this, and from his books. And at the bottom right there, posters. He made posters on poster board with marker by hand, drawing slowly, straight edge, and this is one of them. It's about that big, and this is one on kind of the life cycle of the universe. He has another one on the scale of space, and the amazing thing is he made all of these, and he did not feel the need to put his own name on it. He did it purely for the joy of physics, joy of astrophysics, but he did always give credit where it was due. And in this particular poster, if you look at the bottom right, 5 ages of the universe, Fred Adams. So I think it is very fitting that the inaugural speakers for the annual Pulikeshi Dayalu Astrophysics Lecture should be one of his favorites, Fred Adams. Thank you. Thank you all.
Hi, thank you very much for that wonderful introduction to your father and his interest in Saturday morning physics. My name is Rachel Goldman, and I'm a co-organizer of the Saturday morning physics this year. I'm a professor of material science and engineering and physics, and I have the great pleasure to introduce to you today's speaker, Fred Adams, the Tao Yu Wu Collegiate Professor of Physics here at Michigan. Professor Adams has been at the university since 1991, and he's received numerous awards, including he's a fellow of the American Physical Society, and he is currently the director of the Leinweber Center for Theoretical Physics. He's going to tell us today about the formation of planetary systems, and I know all of us are really looking forward to his lecture. So without further ado, I'll give it to Fred.
So good morning, everybody. So today I want to tell you about how planetary systems come to be. So let's jump right into it. Since I'm going to give a very jumbled presentation, let me start by giving you a brief outline of the basics. So what I want to do is I'm going to give you a brief whirlwind tour of all the planets that we found in the last couple of decades. And then I'm going to review the birth environments of these planets. Spoiler alert, they happen in disks that I will tell you about. Now, it turns out that there's two different ways to make planets. You can make them from the top down and from the bottom up. And I will tell you about both of these mechanisms and tell you which one is the most important. And then at the end, I'm going to tell you about what planets look like when they're in the process of forming. And this is kind of the current state of the art, the cutting edge, what we're just on the cusp of being able to do. So let's jump right into it. Over the last couple decades, we have found over 5,000 planets orbiting stars other than our sun. Now, this plot here tells you kind of sort of where they are. So what we do is we plot the location of the planet on the horizontal axis and the mass of the planet on the vertical axis. Now, just to ballpark everybody, we measure distance in AU, and AU is an astronomical unit. It's the distance from Earth to the sun. So Earth is at 1. This is Earth. And then we measure mass either in Earth masses or Jupiter masses. Because of the way people do these things, we go back and forth between the two units. The thing you need to know is that there's 316 Earths in a Jupiter. So those are our units. And you see that we see planets really close to their stars and really far away from their stars at really low mass and at relatively high mass. There's many orders of magnitude in all of this. And the planets that we see sort of span all of the space, but not quite all of the space. There's these blue parts where we don't see very many planets. And there's a reason for that. The planets that are in this blue patch here are close to their stars. And the reason why we don't see very many there is because when they're that close to the stars, they get hoovered into the stars and they get eaten. And there's a few on the way in, but we don't expect to see many, and we don't. The reason why we don't see any here in this region is because they're small and they're farther away. And that just means they're harder to see. So we don't expect this space to be empty. It's only empty because we haven't got around to seeing it yet. Now you see that this line here kind of goes right through Earth. We're right now with the current technology, we're able to see Earths, but just barely. And that's just where we are. And over the coming decades, we will see more and more, and we will fill in this space here. Now, another way to look at the planetary sample is to plot, instead of the mass on the vertical axis, we plot the eccentricity. And you see that we see the same wide range of locations in semi-major axes. And there's a lot of low eccentricity planets, but there's some high eccentricity planets. And again, this region over here is not populated because that's the population, or the part of the parameter space, where the star squeezes the planets and sucks them in, and they shouldn't be there. And guess what? They're not. So that actually kind of makes sense. Now, for the next few minutes, I'm going to give you basically some distributions of these planetary properties, and this will set up the formation problem that I want to talk about. So the first thing that you might want to know is what's the distribution of masses? So this is the way astronomers plot it, and it doesn't really mean much to you, so let me tell you what it means. Basically, we plot the mass in bins in logarithmically spaced bins, and this curve is basically flat. It's flat in logarithmic space, which means in terms of number, the number of planets goes like 1 over the mass. That means there's 10 times more planets, 10 times bigger than Jupiter than there are Jupiters. There's 10 times more Jupiters than things that are about the size of Neptune. And that's basically where we are for large planets. But if we zoom out and we look at all the bodies, this is what we see. So this is mass from 10 Earths to 1,000 Earths to 10 to the 5 Earths to 10 million Earths. 10 million Earths is kind of a silly way to talk about masses, but those are the very biggest stars. So this red curve here is the distribution of masses of stars. This dotted line here is the distribution of bound planets, and there might be freely floating rocky debris that extend up to even smaller masses. But there's a lot of information here. But what I want you to take away from this for today's talk is that stars are here, planets are here. There's kind of a peak, and the peak is at about 10 times the mass of Earth. So think about that mode. Planets want to be in a size that's 10 times the mass of Earth. Now, the first thing you're going to say is that, well, our solar system doesn't have any planets that are 10 times the mass of the Earth. I'll let you ponder that mystery, and then I will reveal the solution in a little bit. But before I do that, let us continue our survey of planetary properties. Another thing we see, which is kind of cool, is that when we look at multi-planet systems, we can plot the size of the planets as the size of the dots. Each one of these lines is a planetary system with 3, 4, 5 planets. And what you see when you look at this picture just visually is that in a given system, all of the planets seem to have pretty close to the same mass and very regular spacing. Now, from system to system, the masses are bigger here and smaller here, but within the same system, there's a certain amount of regularity. Now, this isn't just a trick of the eye. You can actually do the statistics, and you see that there's a very, very close correlation between the sizes of planets within the same system. We call this phenomena peas in a pod because they're like a bunch of peas that are very much like each other in the same system. So the lesson here is that in spite of the huge diversity that we saw in the first slides, there's also superimposed on that a certain amount of regularity that we see in planetary systems. So there's always this compromise between lots and lots of variety and yet regular order that shows up in these systems. Just to finish the story, if we plot the distribution of separations, we see there's a nice peak so that they're regularly spaced. We can also do the same thing in period. Now, the final thing that I'll tell you about is where are the planets? Well, we have a problem here because it's a lot easier to see the planets close to the stars than farther away from the stars. But what we really want to know is what's the distribution of planets, how likely they are to be, how far from their star. So you have to do a lot of work to put in the planets that are not seen, in other words, to deal with what are called selection effects. So when you do that, I'll show you 3 different versions of it. Here's one, here's 2 more. And if you go back and forth between them, different groups have done this different ways, but they all find the same thing. And what they find is that the distribution peaks at 3 to 5 AU. In other words, the most likely place to find a big planet is at 3 to 5 AU. Now that actually kind of sort of makes sense, because if you look at our solar system, the biggest planet is called Jupiter, and it lives at 5 AU. So what is emerging from this is that 5 AU is the sweet spot for making planets. Now, we actually thought that was the case back in the 70s, which is longer than many of you remember. But then when we found the first planet, we found that they were in close orbits. So people sort of started to doubt what they knew. But now that we've found 5,000 planets and we can do the full distribution, we find the sweet spot is back at 5 AU. Now, why does that make sense? Well, the reason is this. As you'll see, planets are made from little tiny rocks. And close to the star, rocks are hot. Far away from the star, the rocks are cold. If the rocks are cold, they have ices on them. If the rocks are hot, they don't. So when you go outside in the winter, you can make snowballs because icy things stick together. And as a bonus, there's 3 times more mass when you have ices than when you don't. So if you make a planet in the outer solar system where it's icy, things stick together and you got 3 times more mass. If you make a planet in the inner solar system, it's like trying to make a sandball at the beach. It doesn't work very well. So the story is that the sweet spot for making a planet is just outside the ice line, we call it, which means you're just far enough out in the nebula that all the rocks have ices on them. And that's exactly what the distribution shows. That's exactly what we see in our solar system. So now, with this whirlwind tour of the data, what we want to do is we want to ask the question, how do solar systems get formed? How do planets come to be? In other words, if we take all the raw material that we see, how do the little mechanisms, the levers and pulleys work that actually construct the planetary sample that I just gave you an overview of? So, our story starts in great big clouds far, far away with the formation of stars. Stars form in what are called molecular clouds, which are great big clouds of gas. They have masses of about 1 million times the mass of the sun. We can study them because stars are forming today, and we kind of know how the process works. Now, this seems far removed from planets, but let me connect the dots. So within these molecular clouds, which, as I said, are millions of times bigger in mass than the sun, there are subregions that form clusters of stars. And in the clusters, we form individual stars. So the individual stars go through this process where you have a clump of stuff that's several times bigger than a star. It collapses from inside out, and then it forms a disk around it. So you get a star and a disk of material. And then the planets form inside these disks. So the star formation problem, or the star formation process, provides the initial conditions for the process of planet formation. Here's another artist rendition of the same thing, where we start with a cloud, and the reason I'm showing you this is just to give you the scales. The cloud itself that contains a couple solar masses worth of material has the size of about 20,000 AU. While it's collapsing, it gets smaller, and when it forms a disk, it makes a disk. This plot says 50 AU. As I'll argue in the next slide, there's actually a range of sizes that goes from about 10 to 100 AU. So the point is this. When a star forms, it's spinning too fast for all of the material to fall all the way to the size of a star. So instead, it collects in a circumstellar disk, a flattened structure that looks a lot like a solar system. And just by coincidence, or maybe not by coincidence, the size of those disks is always in the range of 10 to 100 AU. Now, before we could actually look at disks, we thought and we predicted that the disk would be 10 to 100 AU in size. Your first guess is that what's the size of our solar system? Well, Neptune's at 30 AU, so 10 to 100 AU is a pretty good guess. But if you look at the radiation coming out of forming stars and newly formed stars, in order to understand the radiation signature, you expect the disks to have sizes of about 100 AU. Second, you can measure how fast these clouds are spinning, and then you can just calculate, based on conservation of angular momentum, how far they should collapse. And the answer you get, again, is 10 to 100 AU. But then the cool thing is that we can now actually just look at them. We now have the technology just to make a map of a disk that's forming. So there's an interferometer on the Atacama Desert in Chile, and I'll show you another picture in the next slide. And we wire together these telescopes to give you very high resolution, and you can actually take a picture of a disk. And when you take a picture of the disk, what you get is that the size is 100 AU. And this is exactly what we predicted in 1987 for this exact same source, okay? Now, this is not just a one-off, but we can measure a whole gallery of different disks, and there's a picture of the interferometer in Chile, and here's a collection of the disks that is found, and they're all about 100 AU in size, okay? So, We know observationally that the starting point for forming planets are in these disks, and the size of those disks is very close to the size of solar systems, namely 10 to 100 AU. But that's not the only thing we want to know about them. We want to know how much mass are in them. Now, calculating the mass in a disk is actually a lot of work. And it's a little bit of an art as well as a science. But the bottom line is this. We can plot the mass of the star on the mass of the star on the horizontal axis and the estimated mass of the disk on the vertical axis. And you see there's an upper envelope. And the upper envelope corresponds to a simple law where the maximum disk mass you can have is 10% of the stellar mass. You can, instead of looking at the mass, you can look at the mass accretion rate and turn that into the same limit, and you find the same result. So the bottom line is that when disks form, they have less mass than their stars. The most mass they can have is about 10% of the mass of the star, and then it gets smaller from there. Now, to ballpark you, we have a benchmark in this business called the minimum mass solar nebula. If you take all the planets in our solar system today, and you say, well, they're mostly rock, so the gas is missing. So we'll put the gas back in, just in our minds. And if you do that, you get a mass estimate for how much mass the disk had to have. And it's the minimum, because that's the minimum you have to explain the planets. You could have more and get rid of it, but you need at least that. And that number is about 3% of the sun. So what emerges from the observations is that we see disks with a maximum mass of 10% of the mass of their star, and then we need about 3% of the mass of the star to make solar systems, and that actually makes perfect sense. And that's the starting point for the planet formation problem. Now, the other thing we need to know is how long does it take? Well, these disks don't live forever. If you look at old stars, they don't have disks. Only young stars have disks. So what we can do is we can plot the fraction of disks as a function of age of the system, and Jesus Hernandez made the canonical plot of this, so this is like a classic result. And the data show the fraction of systems with disks as a function of age, and what you need to know is that the age is measured in millions of years. It turns out that this distribution is very close to an exponential, so the disks have a half-life. And the half-life is about 3 million years. In other words, if you have a bunch of disks, after 3 million years, half of them are gone. After another 3 million years, another half of the half are gone, and you're left with a quarter. After 9 million years, which is 3 half-lives, only 1/8 are left. So only 10% of this disks, give or take, will live for 10 million years. So by the time you're at the 10 million year age mark, disks are kind of out of business. So that means this whole planet formation process has to play itself out on timescales of millions of years. This plot just shows that you're very close to an exponential. Now, the other thing that you care about, and this is getting a little bit in the weeds, but let me explain it for a minute. We care not just about the mass and the size of the disk, but we care how the mass is distributed. So we describe that with what's called a surface density, and the surface density looks like a power law with some index. And we can measure that index in a whole host of different ways. And we always get an answer that's between 1 and 2. What that means is that the density of the disk is very large, close to the star, and it gets smaller and smaller as you go away from the star. But because these power laws are not that steep, it means most of the mass is in the outer disk. So if you want to make big planets, you have to go to the outer disk. So if you summarize, the starting point for the planet formation process is the circumstellar disks that form alongside their stars. And we know their properties, and we don't just know their properties, we can actually measure in detail the distribution of their properties. And I've given you sort of a whirlwind tour of that, but we kind of know where our starting point is. And the starting point is that the disks have radial sizes of 10 to 100 AU. They have masses that are 10%, 5% of the mass of their star. They have surface density profiles that decrease outward, and they live for a distribution of times, but the half-life is about 3 million years. That's also the median time. So the planet formation process has to play itself out in millions of years. The other thing, if you take all of these data at face value, it suggests that as the disks evolve, the dust and rocky stuff moves in a little bit, and the gas moves out a little bit. That's less clear from the data I showed you, but that's what we think happens. So we're kind of a half hour into the talk now, so it's time to start. So the point of this talk is to tell you how planets form. So it turns out there's two different methods or two different mechanisms to make planets. As I said earlier, you can make them from the top down, or you can make them from the bottom up. Now, when I say you make them from the top down, what do I mean? I mean that we have these disks, and if they break apart into fragments from the large scale of the disk to smaller bodies, they can, in principle, form secondary bodies, and that could, if the process works well enough, form a planet. The other mechanism is to start with the little tiny rocks and build them up, and then let the rocks get bigger and let the rocks eat gas, and finally you'll end up with something that looks like Jupiter. So you can go from the bottom up to Jupiter or from the top down to Jupiter. The question is which one works best, when does which one work, and how. So the story is this. If you dial back to before I came here, which was a really long time ago, as you heard, I was working with Willy Benz at Harvard, and we were trying to form binaries in these disks. In other words, we were trying to make these disks fragment into stars. Turns out that doesn't work, because there's never enough mass in the disks to make a whole star. But we could get a disk to fragment into a little, this is just a 35-year-old simulation of a disk fragmenting into a secondary body. And it turns out that because the disks have a tenth of the stellar mass or even more, you can't form a small body like Jupiter, but you also can't form a big body like a star. The only thing you can form is something that's in between. The thing in between a planet and a star is called a brown dwarf. It has a mass of 10 to 20 times the mass of Jupiter. And moreover, because all the mass is in the outer disk, like we were talking about earlier, the things form in the outer disk, but the disks are 100 AU in size. So the top-down mechanism naturally produces brown dwarfs at 100 AU. And we knew this in 1990 and 1991, but we had really, I think the word is crappy, computers, and we couldn't really say this. So Zhao Anzhu, who is a grad student here, 20 years later, did a beautiful set of simulations. He wasn't the only one, he was just the best one. And what he did is he did a whole suite with very exquisite numerical resolution, and he did lots and lots of work and burned up lots and lots of computer time, and what he found was that these disks fragment into brown dwarfs at 100 AU. Sound familiar? Now, it turns out that when we look in the sky, we can sometimes image planets. Here's a famous planetary system that you might have seen. It has this phone number, HR8799, but it has 3 planets in it, and they're basically brown dwarfs at 100 AU. They're a little bit smaller than brown dwarfs and a little bit less than 100 AU, but close enough for government work. So what we see is that if we look at the gravitational instability mechanism, it works, but it produces brown dwarfs at 100 AU. So sometimes it works, but it has a low duty cycle. And what that means is that most planets form in a different way. So if I go back to the plot I started with here, where I plotted the whole sample of planets, the things in the square are the brown dwarfs at 100 AU. These are the image planets, which are the purple ones, and these are the ones that we think formed from the top down. These are the ones that we think formed from gravitational instability in the disk. So this channel of planet formation does in fact work. It just only works in this box, which is great if you live in the box. But what about all these other planets? So we need a second mechanism to form all the other planets. And the second mechanism is what we call the core accretion paradigm, which basically means from the bottom up. So in a broad brush sense, here's how it works. We can imagine that planet formation from the bottom up happens in 3 phases. The first phase is you make a big rock, okay? Now, I want to emphasize to you, you've got a long way to go, because in this cloud we started with, the million solar mass cloud that made the star, all the rocky things are in the form of dust grains, and the dust grains have a size of about a micron, and you can ask, well, what's a micron? A micron is 10 to the minus 4 centimeters. So it's 1,000 times smaller than a millimeter. You could almost imagine it, but it's really small, right? So those little small dust grains, we call them, have to somehow form a planet or a big rock, a planetary core, that's 10 times the mass of Earth. That's almost so big it's hard for you to imagine. So we start with things that are almost so small you can't imagine them, and go up to something that's almost so large that you have a hard time imagining it. So that's step one. No problem, right? Now, once you get to the mass of 10 Earth masses, that's sort of a magical mass scale, as I'll emphasize a couple times. But what happens here is that once the rock has 10 Earth masses, it's got enough gravity, it has strong enough gravity that it can hold on to gas. Our Earth has a little bit of gas, but you probably know the Earth's atmosphere is sort of nothing compared to the mass of the whole Earth. It's just a little tiny skin. But once you get to 10 Earths, the gravity is strong enough it can eat a lot of gas. So if you want to make a big planet like Jupiter, you have to get to that stage where the rock is eating gas, and that's stage 2. But stage 2 has a problem. It turns out that when you accrete the gas, it gets hot and it gets puffy, and as I'll explain in a little bit more detail in a minute, it's hard for the planet to eat more gas. You have to wait a long time for the gas to cool so more gas can come in. So there's this long extended phase called phase 2 where the planet is eating gas, but only very slowly. And then a miracle occurs. Once the atmosphere is massive enough, its self-gravity is strong enough that it can smush itself. That's the technical term for it. It will collapse under its own weight. And once it does that, it can eat gas rapidly, and then the planet can grow rapidly and become as big as it wants to. So that's the phase 3. So we have these 3 phases, which we can write schematically this way, and this way, and that's how planets form. So what I'm going to do for the rest of the talk is I'm going to fill in the detail, or at least some of the detail, of how these 3 stages work. Just to give you the time scales, the growth, what I'm showing here is the rock mass, the gas mass, and the total mass as a function of time in simulations of this process. And what you need to know is that it takes kind of sort of 1 million years-ish for the rock to build. And then it takes a long time, millions of years, for the big rock to slowly gain gas. And then right at this arrow here is where the miracle occurs, like I said, and the atmosphere collapses and the gas can accrete rapidly. So we have phase 1, rock building, phase 2, slow growth, and phase 3, rapid growth. Most of the time is eaten up in phase 2. Most of the mass is accumulated in phase 3. So let's go through this process in a little bit more detail. So like I said, we need to start with rocks. And when you first make this, the disk, the rocks are in this in the state of little tiny dust grains, a micron in size. And they have to somehow get up to a 10 Earth mass rock. So we can go through the details of the math, but we're not going to do that today. Let me just give you the broad brush picture. So the first step is this. If you have these little tiny rocks, and they have ice on top of them, because we're doing this in the outer nebula where it's cold, those things will accumulate. And they will accumulate pretty rapidly and pretty readily until they're about the size of gravel. So it's actually very quick and very natural for these little tiny dust grains, which have ices on them. Once they get in a dense nebula, they will stick to each other, and they will create little icy snowballs about the size of gravel. Maybe even as big as a whole snowball, so maybe 10 centimeters in size. And that happens rapidly. Now, they still are dense, and there's a lot of them, so they'll still collide. So it would be natural if they continued to hit each other and grow larger. But then there's a problem. And the problem is this. Once the rocks get to be about 1 meter in size, so we're talking this big, when you smash them together, instead of getting bigger and merging, they break apart. which is a problem if you want to make bigger things, right? So in the business, they call this the meter barrier. It's hard for rocks to get bigger than about 1/10 of a meter, because when they get to be a meter in size, then they hit each other, they break apart, and you have to start all over again. So something else has to happen. Now, what has to happen is a little bit subtle, but let me try to explain it to you. What happens is that we have all this gravel, so rocks that are kind of the size of rocks that you can hold in your hand, and they accumulate, and they get concentrated. And they get concentrated in such a way that there's sort of equal amounts of gas and rock in the midplane of this disk. And under the right conditions, you can jump over the meter barrier because there's something, sort of miniature version of a gravitational instability, like the one that formed the big planets early on, only this is happening on a small scale. And what it does is it takes all those rocks and it puts them together into a secondary body. And the process is a little bit complicated, but it's basically a gravitational instability in the rock fluid, where the rock fluid is a bunch of gravel. And when the disk undergoes this instability, what it does is it produces rocks or rocky bodies that are about 10 to 100 kilometers in size. We call these things planetesimals because they're sort of like things that will be planets. But they're also known to you as asteroids, right? These are kind of the things that you don't see. So the prediction is that we jump the meter barrier because the disk first makes gravel, then it undergoes this instability, and then we have 10 to 100 kilometer sized objects. And that these are the building blocks that will eventually make the big planet. Now let's see if that actually makes sense. Well, I'm going to tell you now about a Michigan experiment that gives us some information on whether or not what I just told you is true. So what you need to know is that if I look at our solar system, we have the planets in here. There's Jupiter and Saturn and Uranus and Neptune. And outside of Neptune, there's a bunch of little rocks. They're not asteroids because they're not in the asteroid belt, so we call them Kuiper Belt objects because they're what's in the Kuiper Belt. We also call them trans-Neptunian objects. But these are a bunch of rocky debris that's left over from solar system formation. So if the story that I just told you is true, then out here, beyond where the planets form, there should be leftover raw materials from the planet forming process, which should be 100-kilometer sized rocks. Okay? So the question, are there? Well, it's actually hard to see rocks that are as small as 100 kilometers. You need a big telescope, and you need to look for a long time. But there's a problem. You can see things that are fainter if you look for a long time, but if you look for a long time, since these rocks we're looking for are in the solar system, they move. But if they move, then they're not in your field of view anymore, and you can't look for a long time. So how do you deal with this problem? Well, like all things in physics, the way you deal with this problem is you get a grad student. And this is where Kevin comes in. So what you do is you take bunches of pictures, and you take them for long enough that the object doesn't move during the time the picture is being taken. And if you knew how the object was moving through the sky, you would just take a picture and you'd take the next picture and then you'd shift it back and add it, and then you'd take the next one and shift it back and add it, and then you take the next one and shift it back and add it, and you'd build up a nice picture. The problem is you don't actually know which way the thing's going. That's why you need Kevin. Because what you have to do is you have to look for all the possible ways the thing could move and stack them together in all the possible ways that it could work, and then find the one, that, if any, that works. And when you zoom in on it, this is like a collection of different things. So if you don't stack right, you get a mess, but if you stack right, you get a nice, beautiful picture. So as part of the DEEP collaboration, which is a collaboration between Michigan, Northern Arizona, and the University of Washington, we found 2,300 of rocks this way. And this was part of Kevin's thesis, who graduated earlier this year. And if you take the 2,300 pictures and you put them into one big picture, this is what you get. So each one of these little pixels is a new discovery of a rock in the outer solar system. They just happen to show this pattern. Now, this is probably not the best way to display the data. The best way to display the data is to actually plot the distribution of sizes. We actually plot them by their brightnesses. Brightnesses increase to the left, so the smaller, dimmer ones are on the right. And this data shows the distribution of the objects. Just to orient you, everything to the right of this line here is sort of new, as in, until this shift and stack technology, as we called it, we couldn't see things to the right of this. With one exception, a former professor here named Gary Bernstein found one point out here with the Hubble Space Telescope, but only one because it required the Hubble Space Telescope and you only get so much time. But except for Gary's point, all of these guys are new. And what you see is that there's a nice distribution. Now let me zoom in on it and tilt it. So why is this important? Well, if you just had a smooth distribution with no structure, you would get the purple line, which is straight. The three colored lines that aren't purple correspond to different versions of the same distribution that has a scale associated with it. And it's kind of subtle. It doesn't really stand out. But there is a difference between the purple line and the other three lines. And the data fit the other three lines better than the purple line. And that means that there's evidence, you could do the statistics and show this is true, there's evidence that there's a scale in this data. And the scale in brightness corresponds to a scale in size, which is, wait for it, about 100 kilometers. In other words, the distribution of these rocks that Kevin found is exactly what you expect from the streaming instability. So we have further evidence in our own solar system from a Michigan experiment that the rocks accumulate according to this instability. So we can kind of take it to the bank, or we want to take it to the bank, that the rocks have accumulated into 100-kilometer sized bodies. Now then, the 100-kilometer sized bodies will collide with each other. And when they collide with each other, with such large sizes, the gravity is strong enough to hold them together. So even though they bash together and they break apart, the gravity holds all the pieces together. So you get bigger and bigger bodies. So also, these large bodies are big enough that any of the little gravel pieces of rock will also accumulate. So you have sort of two competing effects that are making the rocks bigger. The big things are colliding with each other and merging, and then they're hoovering up all the leftover gravel. And they get bigger and bigger and bigger, and then they get bigger and bigger and bigger. Now, where does this end? Why don't they just keep getting larger and larger and larger? Well, two important things happen. Once you get to about 10 times the mass of Earth, it's hard to grow larger. Because once you get rocks as big as 10 times the mass of Earth, they're sort of rare, so they don't hit each other very often, so it's hard to get bigger by two-body collisions. It's also harder to eat gravel, or to accumulate gravel, because the big rock will attract the little rock and the gas along with it. But it will do it so fast that the rock will shoot out the other side and not be accreted. That's not obvious, but you can actually do the math and put a formula on it, which looks like this, but the mass you get is about 8 to 10 times the mass of Earth. So it's really hard to build rocks that are bigger than about 10 Earths. At the same time, once you do get to a rock that's the size of 10 Earths, it's got enough gravity to hold onto gas. Now remember, out in space, there's 100 times more gas than rock. So once the 10 Earth mass rock is big enough to accumulate gas, 99% of what it accumulates will be gas and not rock, so it doesn't get any bigger in rock, it just eats gas. So to a first approximation, we think that 10 Earth masses is sort of a fundamental size scale, a fundamental mass scale, that every rock in the universe wants to be in the form of a 10 Earth mass rock. Because things will just keep getting bigger, but there's 3 reasons why you can't go beyond that limit. So that would make sense. But then you say, and we mentioned this earlier, what about our solar system? Why don't we have any super Earths in our solar system? Well, the answer is we do. We have 4 of them. The cores of the giant planets are actually super-Earths. Jupiter, Saturn, Uranus, and Neptune have a core that's about 10 Earth masses in rock, perhaps another 10 Earth masses in ice. And in the case of Jupiter and Saturn, there's gas on top of them. In the case of Uranus and Neptune, there's not. Their total mass is about 17 Earths. So it's just rock and ice. So if you take the rocky content of our solar system, this is what you get. This plot shows where the area represents the mass in rock in each of the bodies. So we have Jupiter and Saturn and Uranus and Neptune, which are all 15 to 20 Earth masses of ice and rock. And you see that's the vast majority of all the rock in the solar system. Earth has, it turns out, 1 Earth mass of rock. And Venus also has about 1 Earth mass of rock. So you see this is a tiny fraction of the total, just a few percent. And this little tiny sliver here, that's Mars. Mars does not matter. Mars isn't even really a planet. I mean, it just is, it's just a leftover thing. So in terms of the rocky inventory, Mars doesn't matter. Everything's in super-Earths. So that's one lesson that you should take away, is that rocks want to be in the form of super-Earths. That's the natural size scale you can build up to. It's hard to build up further than that. And as I just argued, our own solar system is actually dominated by super-Earths. So to summarize, there's actually 3 size scales that happens in rock accumulation. The little tiny dust grains we started with end up in gravel readily. They just collide together in the way you would expect them to. Then this instability binds them together into 10-kilometer size planetesimals, which are basically asteroids and the TNOs we see today that are left over. They will naturally want to get bigger, but they can't get bigger than about a super-Earth or 10 times the mass of the Earth because of all the reasons we just went through. So these are kind of the 3 preferred size scales that rocks like to live in, but most of the mass actually happens in the biggest one, or most of the mass actually resides in the biggest one. So what happens next? Well, we now enter phase 2. The rock is now 10 Earth masses. It can start to accumulate gas. So here's the middle of the rock, and then there's a boundary. Outside the boundary, the material doesn't belong to the planet, it belongs to the star. Just like if you're out in space, if I drop something, it falls to Earth. But if I go far enough away from Earth and I drop it, it will fall to the sun, not to Earth. So there's kind of a boundary between what belongs to a planet and what belongs to the outer solar system. The boundary kind of looks like this weird eye-shaped thing, but to 0th order is the sphere. And inside the sphere, stuff falls in. Outside the sphere, stuff doesn't do anything. So when we reach phase 2, cool and condense, and then more stuff can come in. And then it will cool a little bit more, and more stuff could come in, and so we go. And so it goes. But the problem is that's slow. That's why it takes a long time for gas to accumulate during phase 2. But once enough gas has gotten inside the boundary, its gravity of the gas itself is enough to compress it, and then we enter into phase 3, where material falls in rapidly. Okay? So what I'm going to tell you about for the next 5 minutes, which is the last part of the talk, is what things look like during this phase 3, okay? So the picture that you should have in mind is we have a star, we have a disk. I'm just showing you a cutout of it, and there's a sphere of influence that belongs to the planet, and a planet's forming at the center of the flow. There's actually 3 outer boundary conditions that we have to worry about, so we're not going to worry about any of them. What you need to know is there is a sphere of influence. All 3 boundaries are actually about the same size. And they're also about 1,000 times bigger than the size of the planet. So you have the planet itself, which is kind of planetary size. You have the sphere of influence, which is hundreds of times, maybe 1,000 times bigger. And then you have the outside disk. So what happens is that the disk itself feeds material into this region, and that falls to the planet. And we want to see, well, what does that look like? And I'll tell you why in a minute, but let's just see what it looks like. So you can actually solve for what the trajectories of these infalling parcels of gas look like. And what I'm showing you here is the projected trajectories of this infalling. gas. And it doesn't look very interesting. They almost look like straight lines, but they're actually curved. And since I'm showing you the projection, as these things fall in, they actually spiral around, which I'm compressing. So the actual picture is actually even more interesting than this. But the point I want to emphasize is that the trajectories along the equator don't go all the way in. The trajectories along the pole do go all the way in. So the planet itself is down here, but the stuff that comes in along the equator can't fall all the way in. So what happens is that the planet itself produces its own little disk. Remember, when we made a star, the star had too much angular momentum, or the pre-star material had too much angular momentum, so we made a circumstellar disk with the size of 100 AU, and the planets are forming out of that circumstellar disk, the big disk. But the planet formation process itself will make a little disk. And the little disk is a third of the sphere of influence in the idealized sense, and that's about 200 times the radius of the planet. So the point is we naturally get disks. And just like we need to characterize the circumstellar disks that are the birthplaces of planets, we need to characterize the circumplanetary disks, which you're already jumping ahead in your minds, will be the birthplaces of moons, right? Because we get moons, which are little tiny planetary systems. But I'm not going to worry about that today. I just want to know what the mass budget looks like. So we can solve for the surface density of the disks as they come in. We can also solve for the inner boundary condition. It turns out that the planets will generate magnetic fields, and the magnetic fields will truncate the inner disk, and they will also provide sort of a catcher's mitt, which will collect gas that feeds itself directly onto the planet. So the details are complicated, and we only have a couple of minutes, but what I want to emphasize to you is that the magnetic fields provide the inner boundary conditions. And finally, while this object is forming, it's generating energy, and it's generating energy from a lot of different sources. First of all, the planet in the middle is contracting, so it has its own intrinsic luminosity source. We're making a disk around it, so material's falling from the outside disk onto the circumplanetary disk, shocking and releasing energy. But once material's in the disk, frictional forces, which we call viscosity inside the disk, make it swirl and go inward, which provides even more energy. So you can add up all of these energy sources, and this is what you get. So the next step is to ask the question, what do forming planets look like while they're forming? So the picture you should have in mind very schematically is we have this sphere of influence. Inside there's a planet. There's a disk around the planet. The green arrows show the material falling from the outside disk to the little disk. And then the arrows are the photons coming out. And the photons come out in different colors, which is why I showed them in two colors. But it's actually a difficult calculation to calculate all the radiation that's coming. It's being generated by this planet and disk in the middle, and then it has to work its way out through the envelope, and it will scatter, it will be absorbed, it will be re-radiated, and it's a very complicated process, which I won't go through. But at the end of the day, what you get is you get a picture of how much radiation comes out at what wavelength. So this is frequency. So frequency goes to the right, equivalently wavelength goes to the left, and this is the amount of energy coming out at each wavelength. So optical wavelengths you see are right over here. Most of these things are in the infrared, and some of them are in the radio, as in log wavelength. And you see that in order to specify what a planet looks like while it's forming, you need to say, well, how much mass does it have at the moment? How fast is mass coming in? Where it is? And what its magnetic field is, that's the inner boundary condition. So what I can do is I can calculate the signature of planets as they form, and I'm just going to show you some examples. So here, I'm keeping the accretion rate and the location and the inner boundary condition the same, and I'm just making the mass bigger. And as the mass gets bigger, you see it gets brighter and it gets bluer. If instead I fix everything but the mass accretion rate and increase that, it gets brighter and it gets redder. If I change the inner boundary condition, I get subtle things. If I change the location and I move my forming planet from 5 AU inward to 1/10 of an AU, then the radiation signature gets narrower. It gets to be a narrower range of wavelengths. Now you can ask, why am I telling you this? Why do you care? Well, what you would ideally like to do is you would like to be able to look at planets. I showed you pictures of the disks. What you'd like to be able to do is to have even higher resolution and look for the planets forming in those disks. And if you could do that, then you could measure how much radiation is coming out of those forming planets at each wavelength and compare them to these pictures that I'm showing you. And if you could do that, then you could tell what the properties are of a forming planet. You could test the theory that I'm describing to you in very, very exquisite detail. So here's the thing. You and we live at the point in history where this is now just becoming possible. Right now, in order to do this, we would like to look at a bunch of sources at a bunch of wavelengths and get a bunch of data. Right now, there's one data point, and here it is. And it's not a very clean data point, but nonetheless, this is a map. See, this is like the ALMA maps you say, but if you look in, there's a little tiny little smudge there. We think we have the resolution and the sensitivity to say that that's a real thing. And we can only do this at one wavelength, which is about 1 millimeter, so it's a very long wavelength. And what this thing is, it's one of these little disks that's forming around a planet, we think. So we have one data point at this point in history of a disk around a forming planet. But in the next decade, we hope to have a revolution of this, and we will see many pictures like this, which will be a better, increasingly better resolution, and we will do it at more wavelengths. And then we will have signatures of forming planets in the disks that I showed you the pictures of earlier in the talk. And that's where we're coming to, okay? So I'm 1 minute over, so let me conclude. What I've given you is a whirlwind tour of the current status of the planetary populations that we've observed to date, and then a whirlwind summary of how we think they came to be. And the sort of highlights are written here, so let me just go through them. There's two ways to make planets, but we think most of the planets form from the bottom up through what's called the core accretion paradigm. Now, most of the rocky material lives in 3 different size scales. It lives in gravel, then it automatically becomes planetesimals through this instability, and then the rock accumulates until it's super Earth size, 10 times the mass of Earth. Most of the rock in the whole galaxy wants to be in the form of super Earths. And in our solar system, the vast majority of the rock in our solar system is, in fact, in super Earths. But once the super Earths get big enough, they can accrete gas and form larger planets. These smaller planets we see are just instances of the failure to become a super Earth. But most of the mass is actually in the bigger things. And we can actually understand the distribution of planetary masses in this scenario, although I didn't have time to talk about it. And we also find that planets tend to form near the ice line. Now, there's a whole host of complications, which I didn't have time to talk about. Planets move around, they migrate, they interact with each other, and all of these things. Those things matter, but they don't change fundamentally the basic story that I told you about. So this is kind of the broad brush picture of how we think planets form, at least as of today. And this is a good place to stop. I will take questions.
Okay, we're going to be open for questions. There are going to be 2 people with microphones, and you can line up and ask your questions. I'll get started with some of the questions from online. One question from online is, what keeps planets or more from continuing to collapse? How much condensed matter physics do you need to include?
Well, another way to answer that question is, once you've accumulated matter into a planet, what sets its size? So if you have a planet of rocky composition, then to 0th order, it's just going to have the density of rock, so in very rough terms, it will just have the density of a couple grams per cubic centimeter, just like rocks on Earth. The mean density of Earth just is about 5-point-something grams per cubic centimeter. So it's not all that different. If you instead have rock and gas, then what happens is that the gas has gravity that pulls itself in, but the gas also has pressure, which pushes back out. And you reach what's called a hydrostatic equilibrium between the pressure pushing outward and the gravity pulling inward. And that's what sets the size of objects. And that's why Jupiter is the size of Jupiter. As far as condensed matter physics goes, there's a lot of condensed matter physics that goes into rock composition. I mean, it's very much related to condensed matter physics. And also, in the very densest objects, not the Jupiters, but the things even bigger, the super Jupiters, if you will, the things that have 10 times the mass of Jupiter. Those objects are so dense that in the middle, you have to worry about something called degeneracy pressure, where quantum mechanics gives you an extra contribution to pressure, which is kind of freaky, but it's kind of cool.
Go ahead.
Thanks for a great talk. A few years ago, there was a prediction, I believe by Mike Brown and some collaborators, that there is some sort of massive Kuiper belt object that's responsible for sort of shepherding the other Kuiper belt objects. And I don't know if there's been any sort of progress, or I don't think anything's been discovered, or can you comment if that theory still makes sense?
Yeah, so just so that everybody knows what we're talking about, there's the idea that there's actually an extra planet in our solar system called Planet 9. Since we kicked Pluto out of the solar system, there's only 8 planets, so if you invent a new one, it would be the 9th planet, hence the name Planet 9. And the idea is that it's something like a super-Earth with 5 to 10 times the mass of Earth, and it lives at in a distant orbit at a radius of about 500 AU. Now, why would Mike Brown say that? Well, the idea is this. These Kuiper belt objects that I showed you, 2,300 of them, there are actually some that are bigger. And a small subset of them have really long, skinny orbits. And the first 6 of those long, skinny orbits that were discovered were all pointing in the same direction. See, a circle doesn't have any direction. If you have an ellipse, it has a direction. So the first 6 long, skinny orbits were all pointing in the same direction. And then Mike and his colleague, Konstantin Batygin, put forth the idea that something had to line them up. Because if you just leave them, they'll actually precess and they won't stay lined up. So you need to line them up. And the idea is that the inner planets, which means Jupiter through Neptune, will cause them to precess one way. So you invent a new planet that's outside of them to precess them back the other way and compensate. That's where you get the size and the orbit. So does this make sense? Well, yes and no. After the original 6, there's now about 20. But the 20 are found from 3 different surveys. So on the plus side, all 3 surveys would predict the same Planet 9. On the negative side, each survey only has about 6 things itself, and the statistics are so poor that it's only a 1 or 2 sigma alignment. But on the plus side, another prediction of the Planet 9 hypothesis is that it should kick some of those Kuiper belt objects up to really high inclination objects. In fact, we found one in the DES survey. It's called BP 519, and it's the highest inclination object that we see, and it's at 60 degrees. And the Planet 9 you need to explain the high inclination object we see is the same Planet 9 you need to explain the alignment. But there's not enough statistics in the alignment to say that it's real. On the other hand, if you look at all 20 of them, the ones that are not very well aligned are actually unstable and they move around with time. The ones that are stable tend to be the ones that are the most aligned, which is an argument in favor of it. So back and forth we go. Clearly the answer is we need more data. And there's actually a survey going on called LSST that's just starting, and over the next decade, it's predicted to find like 100 of these objects, or maybe a couple hundred of these objects that have long, skinny orbits. And once you have 100 or 200, then you can either see they're aligned or not, and then we'll know. But until then, we can just fight about it.
Thanks.
Over here.
Hi. This is a rather simple question, but you mentioned that Neptune and Uranus don't have gas.
Not much, no.
No.
They have ice. They're sort of, we call them gas giants, but they're really ice giants.
Okay, and why would they not accumulate more gas? Is there like something in those disks that you were
well,
talking about?
The general idea, which if we had another hour, I could like give you another talk on just this. But the basic idea is that you remember the disks have a lifetime. The plot that Jesus Hernandez showed, they only live for 3 million years. So you have this rock, and it's growing, and it's starting to eat gas. But it takes 3 million years to make the rock, but the gas that it's eating only lasts for 3 million years. So it's a bit of a race. So sometimes the planet wins the race and it can get big and start to accrete gas and get a lot of gas before the disk goes away. And sometimes it loses the race and it doesn't, and it ends up smaller. So within our solar system, we think that as you go further out in the nebula, from Jupiter to Saturn to Uranus to Neptune, the clock that sets this pace of how things accumulate is given by the orbit time, and that gets slower. It's Kepler's law. So Neptune forms a lot more slowly than Jupiter. So the picture that we have is that Jupiter made its big rock fast enough to eat gas while the gas was still there. Neptune did not. It lost the race. And that's a pretty good description of what happens. But there's a lot of holes in that we need to fill in.
So similar to the question, you mentioned that the giants are like 10 Earth mass in rock, 10 Earth mass in ice, and then maybe some gas on top. Why the differentiation between rock and ice? They're both like types of mass, and how does ice treat differently than rock?
Well, in the outer solar system, they're all in it together because the little rocky grains are coated with ice. The reason why we make a distinction astronomically is that it turns out that it's easier to melt water than rock. Yeah. So when you put that into the context of the solar nebula, there's different lines inside the nebula where different things condense. But the big one is at about 5 AU, or 3 AU. Inside of that, all the rocks are bare. They have no ices of any kind on them. But once you're outside about 3 AU, it's cold enough for water to freeze. This kind of makes sense, because Earth's sort of on the border between frozen and not frozen. Today it's frozen, in July it's not frozen, right? So we're kind of on the border. But once you go further out, you're always frozen, right? Now, if you want to melt the rock, you have to go in way inside Mercury. So there's this wide range where you have rock, but no ice. And that's why we make the distinction in terms of composition. But once you have both kinds of stuff, they just collapse together with gravity, and you're absolutely right, that's what happens.
Can I just, Fred, ask, when you say ice, do you universally mean, you don't mean water ice?
Well, I mean water ice, I mean ammonia ice, I mean carbon dioxide ice, and I mean carbon monoxide ice. And it depends where you are in the nebula. As you go outward, first, water ice is a huge thing. There's a lot of mass in water ice out in space. But there's also, if you go further out, carbon monoxide freezes, and there's actually a lot of frozen automobile exhaust out in space.
So you're talking about frozen gases, basically, that can
we call them
sublimate.
frozen volatiles, right.
Okay.
But those are the main important species: CO, CO2, ammonia, and water.
I'm going to ask a question from here, and then we'll go to you. Do or can top-down and bottom-up form planets ever exist in the same solar system?
They could in principle. If it happened in the same solar system, the top-down scenario would produce big planets far away, but that would not prevent bottom-up planets from happening closer in. We haven't actually seen that, but they could see that.
Is anything known about, you had this chart of where the planet is relative to the star, and then the mass of the planet. Where in that region, what would create the environment that would be more conducive to creating life?
Oh, well, the story, the standard story is that if you want a planet that's conducive to life, then you want a planet that's kind of sort of the size of Earth. Usually, people use as a rule of thumb, they want it to be within a factor of 2 in mass of the Earth, which means 20% in radius. And then you want the distance from the planet to its star to be such that the heating from the star is similar to that of Earth in particular, the right amount of heating that water could be liquid on the surface. So the standard astrobiological assumption is that you have an Earth-like planet with more or less Earth mass and radius and more or less Earth temperature. Now, the very first planet of that kind that was found was Kepler 186f, found by another grad student from Michigan named Elisa Quintana, and that was in all the news in 2014. So we have found handfuls of planets that are just like that. But all we know is that they're the right size and the right temperature to have life. We actually don't know the next step, is there life on them? We'd love to know that, we don't.
There's a related question online. If life is more likely to be present on an Earth-sized planet, what is the statistical likelihood of finding Earth-sized planets and therefore life in other solar systems?
Well, the current number is that we define a quantity called eta Earth, which is the fraction of solar systems that have a planet with the properties I just said, namely within a factor of 2 in mass of Earth and a temperature between 0 and 100 degrees Celsius. And the estimates for eta Earth vary widely, but they come in at about 10–20%. So based on the data we have today, which is admittedly a little bit low number statistics. If you remember the plot I showed you in the very first slide, we're just now being able to see Earth-like planets. So in 10 years, I can give you a lot better story. But given what we know now, there's sort of a 10–20% chance that any solar system will have an Earth-like planet. And again, the Earth-like planets have the right size and temperature, but we don't know what other properties are required, and we also don't know what other properties those planets have. That's all to be determined. So this is what you call job security. We have a lot of work to do.
Thank you. So thank you very much. So you started off with this sort of dust cloud picture of gas and dust. So could you sort of explain why the heaviest thing, which is the sun, is formed with the lightest material, which is hydrogen?
Oh, well, I guess the short answer is that most of the mass in the whole universe is in the form of hydrogen and helium. So when processes involve mass, they naturally become mostly gas. And the process that forms a star is the collapse of a whole cloud on very large scales. So mass is driving the whole process, and it's all gas. And that's why the sun is all gas. It has more or less the same composition, 99% gas. In this case of the sun, it's 2% rocks. The rocks aren't rocks anymore, but elements that came from rocks. It has more or less the same composition as the cloud that it formed in and such. To make planets, if you're building them from the bottom up, you're starting with rocks. So to start with, you're all rock. So actually, your point can be turned around and said another argument for why we think the bottom-up scenario, the core accretion scenario, is driving most of planet formation, is that it's starting with rocks, so you end up with things that are a lot more rocky rather than mostly gas. See, gravity and gas are an equal opportunity agent. So if everything formed by gravity and gravitational instability, everything would have solar composition, which means 99% or 98% gas. But since it doesn't, it probably formed from the bottom up.
Can I ask a question?
Just this once, Tim.
Just one more. So a long time ago, there was something that I heard called Bode's Law, which had to do with the ratio of the distances of the planets in our solar system from the sun. That was before all these other solar systems were found, et cetera. Is that still a real thing, and can you understand that, if it is?
Well, the answer is yes and no. So Bode's Law is the idea that the planets in our solar system are regularly spaced. And if you look at the solar system semi-major axis, Earth is 1, Mars is 2.5, Jupiter is 5, which is twice that, Saturn's at 10, which is twice that, Uranus is at 20, which is twice that, Neptune's at 30, close enough, right? So there's a certain regularity that you see. Now, if you go back to the peas in the pod systems that I showed you very briefly, you see that we see planetary systems with 3, 4, 5 planets, which also have very regularly spaced orbits. It's not always a factor of 2. Sometimes it's a factor of 1.7, sometimes it's a factor of 1.9, but within the same solar system, there's a certain regularity. Now, the question is, why? Well, there's 2 reasons that I can give you And we could talk for, again, hours on this. But the short answer is that there's actually a lowest energy state accessible to a system that prefers that state. And second, if you just say, I'm going to take a solar system and I'm going to put in as many planets as I can and have it be stable, you will naturally get a regular spacing. So the picture that emerges is that planetary systems are actually good at making planets. They make lots of planets. And if they make too many, they just kick them out because they're unstable. And what's left will be something that's more or less regularly spaced, more or less like you see.
Thank you for your cogent talk. The core of the Earth is hot and has a lot of energy.
Yes.
Where did that come from? And are all planets have hot cores like Earth?
Well, yes, all planets have hot cores, and where does it come from? Well, if you take two rocks and you let them bash together, they heat up, right? You could rub your hands together and see that friction will dissipate energy, right? So imagine that you have a bunch of rocks that are far, far away, and you put them together to make Earth. Well, that's what we call in physics a lower energy state of the system. So that energy has to go somewhere. What's kind of remarkable is that there's a lot of energy involved in that, and it takes a long time for it to leak out. In fact, it takes longer than the age of the Earth for it to leak out. So that there's still heat in the middle of the Earth that's left over from when it was made. Now, just coincidentally, the time scale it takes for all the energy to leak out of the Earth is more or less the age of the universe. So we're talking longer than 4 billion years, but maybe only 10 billion years. So one of the things that people worry about, for those of you who are going to be here in 5 billion years, is that once all that energy leaks out, the center of the Earth will be a little bit cooler, then plate tectonics will shut down, volcanism will shut down, the planets or the continents won't move anymore, the Gulf Stream will be different, and then we might have a real biological crisis on our hand. The other thing that happens, the other part of your story, is that in addition to everything I just said, there's also lots of radioactive material inside the Earth, mostly potassium-40 and uranium. And the half-lives of those things are also measured in billions of years. So there's enough uranium and potassium-40 and other radioactive species with long half-lives that they're still providing some of the power. Now, I'm not an expert on geology, but that won't keep me from talking. My understanding of the current situation is that the geologists are fighting about exactly what percentage of the heat from the middle of the Earth is that's left over from making it, and that's produced by radioactive species. And as far as I can tell from the outside, it's kind of 50-50. They both contribute. But they fight about whether one's a little bit more than the other, but that's kind of above my pay grade. So.
Was the original source of that energy gravitational attraction between the rocks that came together?
Of the first kind, yes.
In binary star systems, the planetary formation and mechanics differ at all?
What was the last part of that?
In binary star systems, does planetary formation and mechanics vary from ours?
Oh, does it vary? Well, a little bit. So planet formation is kind of a local process. Like I said at the end, we do have to worry about interactions between neighboring planets, and in the case you brought up, neighboring stars, right? So the story is this. If you have a star with a companion, if the disk of material that's making planets is close enough to the main star and the companion is far enough away, you get exactly the same thing. But if the companion is close enough, what it will do is it will truncate the disk of material. So as a rule of thumb, if you want to have a binary close enough to affect, let's say, Earth's orbit, then the periastron of the orbit has to be closer than about 7 AU. But then the question you want to ask is, well, what fraction of binaries are wider than that? And the answer is about half. So most binaries are wide enough that you can make an Earth-like planet without being interfered with by the binary companion. But if the binary is too close, it will basically limit the real estate over which you can make the planets. And the closer it is, the more limitations you get. The other thing you need to know is that about half the stars with masses comparable to the sun are binary, but that means half aren't. If you go to bigger stars, they have a higher probability of being binary, but if you go to smaller stars, they have a lower probability of being binary. And it turns out that most stars are smaller than the sun. If you take the nearest 50 stars, the sun is the 4th largest one. So 90% of the stars are smaller than the sun, and stars smaller than the sun have a lower binary fraction. So most stars actually don't have binary companions, which means we don't have to worry about your question.
Okay, I'm going to take a question from online. Do all solar systems in a galaxy or even the universe spin the same way? Is there net angular momentum in the universe?
The answer is they certainly don't all spin the same way. We don't know that there is a net angular momentum in the universe. We think it's neutral, but we probably don't have enough data to say for sure.
Hi, thank you. Very much a layperson here, but I was curious about when you talked about once the disk forms and half of them go away after a few million years, there's a half-life. What causes those to disappear?
Oh, so why does the gas go away? Well, there's actually a couple of different things. One is the disk has a viscosity in it, which is like the gas is rubbing itself together. And that causes energy dissipation, which means that some of the gas will fall down the potential well. Short answer is it gets hoovered up by the star. Another source of mass loss is that these disks live in very energetic environments, so radiation from the outside will evaporate the outside of the disks, and radiation from the central star will radiate or will evaporate more. And then the third thing is that some of the mass gets incorporated into the planets, like we talked about during the talk. So it's a combination of material falling onto the star, material being flung out from the star or evaporated, and material being incorporated into secondary bodies. And all three of those processes matter, and all three of them conspire to make the disk lifetimes millions of years instead of longer.
Oh, we have one last question from the online. Did Pluto, not really a planet, follow these predicted formation patterns, or are there other theories?
Well, I think that Pluto and the other dwarf planets are just leftovers from the processes that we talked about, and that's the best way to say it.
Okay, thank you. I think we're all done with questions, so let's